All right, so section 4 is on what we call trig identities. And the whole goal of this section, I'll just jump to a problem, is to take something that maybe has multiple trig functions in it, like that, and simplify it as much as you can. To write that in an easier way to understand. That's the goal. There's another one. There's a simpler way to write cosecant times tangent. More compact. And I'm going to show you how we do it. So we're going to be using identities. And I've got a table of them. We've already done some, but I'm going to put the table up on the board for you to write down. So remember, an identity is an equation that is true all of the time. So I'm going to put some identities on the board, and these identities are formulas that work all of the time. They're not formulas that only work some of the time. They work all of the time. So there's some identities that we should already be familiar with. We did not do the Pythagorean identities yet. I just erased them. We're going to do those today. But these we've all done before. Reciprocal, tangent, and cotangent. So let's look at, I think I got one like this one. The one above and the one below are actually repeats, but I'm going to just focus on the one below for a minute. Cosecant. Okay. We don't have a button for cosecant on the calculator. So how do we type cosecant in on the calculator?
1 divided by sine.
Right, it's 1 divided by sine. That is an identity. Whether you want to find the cosecant of 7 or the cosecant of 56.2, you can always do 1 over the sine. Okay, that's always works. How do we type in secant on the calculator?
1 over cosine.
That's 1 over cosine. And if you want to do cotangent, we do
1 over tangent.
1 over tangent. Yeah. So the top one and the bottom one, they're repeats. This is basically saying if you flip sine, you get cosecant. If you flip cosecant, you get back sine. If you flip cosine, you get secant. If you then flip the secant, you get the cosine. Okay, so those are what we call reciprocal identities. Has to do with flipping. Okay, the next ones are the tangent and cotangent identities. If you want to find the tangent, it's the same as the sine divided by the cosine. Let me show you. So let's say I want to do the tangent of 4.6. That's exactly the same as the sine of 4.6 divided by the cosine of 4.6. Sine divided by cosine gives you tangent. So why would you want to do that? That seems more complicated than just writing tangent. Well, you'll see why sometimes we want to write things with sine and cosine, because it's going to cause something to cancel out. Okay, and because tangent and cotangent are reciprocals, if you do cosine over sine, you get the cotangent. Okay, the last group of identities we're going to look at are the Pythagorean ones. These we have not done before. Okay, so somebody pick an angle. Can be any angle you want.
27.
27? No, 27 is good. We can do 27.
27.
So
27.
let's do the sine of 27, and I'm going to square it. And then I'm going to take the cosine of 27, and I'm going to square it. And when I add those up, I get 1. It wouldn't have mattered what angle was picked. 27, 56, 22.4. Whenever you take the sine of an angle and square it, plus the cosine of the angle squared, you always get 1. And the reason that's called the Pythagorean identity is because it has to do with raising something to the second power. So it looks kind of like Pythagorean theorem. Something squared plus something squared. Okay, there's two other Pythagorean identities. They all have a 1 in them somewhere. And then they all have two trig functions that are squared. So the second one is 1 plus tangent squared equals secant squared. And the last one is 1 plus cotangent squared equals cosecant squared. So that's a good list of things if you want to put on your reference sheet, the fundamental identities. I would definitely put those on. Now, one thing we can do with these is we can rearrange them. For example, you can take and you can minus cosine squared from each side. When you do that, you have sine squared by itself, because cosine squared is gone. And on the other side, 1 minus cosine squared. That's the same identity as this one. It's just you move something to the other side. Okay? Same thing with sine squared. If I subtracted sine squared from each side, sine squared would be gone. I would be left with cosine squared on the left. And if I subtracted sine squared, I'd have 1 minus sine squared on the right. It's just like taking the formula distance equals rate times time and writing it as distance divided by rate equals time. But it's the same thing. You just rearrange the variables. Okay? That's all I'm doing here. All right, so any question on those identities, especially this idea of rearranging them? All right, so when we're solving a problem, a hint that you might need to use one of these Pythagorean identities is if you start seeing exponents of 2 popping up in the problem. If you don't see exponents of 2, a lot of times we're probably not going to use one of these identities. Now, the tough thing about identities is there is more than one way to do them, especially as they get more complicated. Okay? Think of it like it's traveling between like 2 cities. If the 2 cities are really close, like let's say Leominster and Fitchburg, there's not a ton of different ways to get from Leominster to Fitchburg. Right? They're very close. You don't have a lot of options. It's pretty easy. They're similar, right? But if you want to go from like Fitchburg to Boston, well, now there's a lot of different ways. There's all kinds of different roads you can take, and there's more ways to do it. So that's kind of how solving identities work. If the identities are relatively simple, there's not a lot of ways to get from point A to point B. There's probably one main way to do it. If the identities start getting more complicated, right, like you're taking a longer journey, now you've got more options to solve the problem. Right? And generally my approach is I try an option, and if I find it's not working, then I go back and I start over, and I try a different way. Right? It's kind of like if you get lost, right? You try one way to get there, it doesn't work. Maybe next time you go, you'll try a different way. You won't do it the same way you did it the first time. So the part that we're doing with these problems is really just the trig part. We're taking a problem and we're going to simplify it. What you would actually be doing with that is calculus. Okay, so this would be like a step before we actually do calculus. What we're doing is we're getting the problem ready to do calculus with it. Right? But we never do the calculus part because this is pre-calculus. So it's the part we would do before we would do the calculus. So if you have to take any math, after this, then you most likely will do the next step if you take calculus. Right? But for us, we kind of stop with what I'm going to show you today. All right, so there's different tricks to try to simplify identities. And one of them is to change everything in the problem to a sine or a cosine. Even if you're not sure how that helps you, you just try it and see if there's something that might cancel out. Okay, what do I mean by cancel out? Well, if you have a fraction and you're multiplying them and you have, for example, the same thing in the bottom and the top, you can cancel it out. Right? That works with numbers. It also works with letters, and it's going to work with what we're doing today. Now, if you're adding, like 3 over 2 plus 2 over 5, no. You cannot cancel the 2's out. The only way you can add fractions is to find a common denominator. All right, so with addition and subtraction, canceling doesn't work. But multiplication, yep, works fine. Okay, so let's try this version. Cotangent divided by cosecant. Let's start with cotangent. Can somebody tell me a different way that I can write cotangent in terms of sine and cosine? I know I can write it as 1 over tangent, but I don't want that. Yep.
Cosine x over sine x.
Yeah. And what's our argument in this problem?
Would it be cotangent? Oh no, theta. Sorry.
Theta, yeah. So whether it's theta or x, just use whatever they use. The argument isn't really important. Just copy down what they use. So it's cotangent is cosine over sine. And how about cosecant? What's another way we can write that one?
1 over sine.
1 over sine. Now, you have a problem that's basically like this. If you want to divide a fraction by a fraction and it was just numbers, how do you divide two fractions?
Multiply.
Yep, multiply the top by the reciprocal of the bottom. Yep. That's how you do that problem. So do exactly the same thing here. Multiply the top by the reciprocal of the bottom. What's the reciprocal of the bottom?
Sine theta over 1.
Sine theta over 1. And now we are multiplying two fractions together. And what's going to happen there?
Sine theta cancels on both sides.
Because we have multiplication, you can cancel the same thing that's in the top and the bottom. And what are you left with?
Cosine theta over 1, so cosine theta.
So yeah, you have cosine theta divided by 1, which is just cosine. So what we just did is we proved that if you have to do something with the cotangent divided by the cosecant, it's much simpler to just say cosine. Cosine means the exact same thing as all of that, and it's a lot simpler. So that's what we're doing today, simplifying trig identities. Okay. Any questions on how we simplified that? Okay. And I could show you they're the same. Like if I put this in y1 on the calculator, and then I put this in y2, they'd look identical. I could show you that. Or you could try it yourself. But graphing is not really the point. Okay, we're never going to graph it. We're going to do what we just did right there. Okay, let's try this one. Cosecant times tangent. Okay, how can I rewrite cosecant?
1 over sine.
Okay, so we can do that as 1 over sine. And how can I rewrite tangent?
Sine x over sine theta over cosine theta.
Sine theta over cosine theta. I think most of my problems today use theta. No, I use t in that one. And then I use an x.
Oh, okay.
It doesn't matter. A lot of them use theta. Okay, so now we're multiplying. What's going to happen there?
The sine theta at the bottom and the sine theta on the top are going to cancel, and we're going to have 1 over cosine theta.
Okay, so we have 1 over cosine. And I would say if you can write something not as a fraction, that's simpler than having a fraction. So what is 1 over cosine? Yep.
Cosecant.
What is it?
Secant.
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 And there you go. Any questions on that one?
No.
No? So again, we took something that started out more complicated. It had two different trig functions, multiplied it together, and using identities, we reduced it down to something that's equivalent, but a lot simpler. Secant. Does So now the next step would be if we had to do some calculus with this. It's a lot easier to do calculus with this than it is with all of that. And they're the same, so you might as well use the easier one. Okay, both of those identities would be, I would consider those easy ones. All right, you pretty much do 1 or 2 steps and you're done. All right, they do get a little bit harder. Some get extremely hard. We don't do any that are like extremely hard, where it's going to take you like pages and pages to figure it out. But we might have some that are like 5 steps. And this was like 2 steps, so we are going to have a few more steps. All right, so the first problem was simplify. The second problem was simplify. We're going to do one in a minute, that is verify. The difference between simplify and verify is with simplify, they give you something and you just keep going till you think you're done. We don't know for sure that we're done here, but I'm telling you, you are done. That is as simple as it gets. Same thing here. We did as much as we could. We ended up with a single trig function. I mean, what else would you do with cosine? How are you going to make it any simpler than cosine? It's just a single trig function. With verify, it's a little bit easier because they give you something to start with. They give you what the answer is. Okay? So they're telling you, when you simplify that, it's going to turn into that. The goal is to figure out the steps in between to go from that to that. Okay? So verify is a little bit nicer because you know when you're done. Right? So again, with verify, you're trying to show that something is true. You got the start, you got the end, you got to figure out how to get there. So the approach that we're going to use when we have a verify problem is you are always going to start with the more complicated side. You never start with the simple side. The simple side won't help you because it's already simple. There's not enough there to work with. The complicated side has more in it, so there's more stuff we can do. So you always start with the complicated side and you work with it until you turn it into the simple side. And there's other approaches, which I'm not going to get into, but that's how I'm going to do it with you guys. So one approach, simplify the complicated side until it turns into the simple side. All right. Now, what did I say earlier? If I wanted to take and add those up, what would I have to do?
Find a common denominator.
I would have to find a common denominator. Well, the common denominator, a lot of times, it's just the product of the 2 denominators, so 14 in this case. So to make this fraction have a 14 in the bottom, what do you have to multiply 2 by?
7.
The other denominator. And to make the denominator on the right a 14, what would you have to multiply that by?
2 the other denominator.
Other denominator. So when you are finding a common denominator, which is another trick that we're going to use, you multiply each fraction by the other denominator. Doesn't matter if that denominator is a number, a letter, or in our case, it's going to be a trig function. Now, I'm not saying that every single identity problem is now going to have to do with common denominators. No, first 2 didn't. We didn't have to do that at all. But it's just another trick that could come up that we can use.
That one's just for addition and subtraction, right?
Yeah, it only applies when you have addition or subtraction of fractions. So when you first look at example 3, you might not be thinking common denominator at all, right? Because there's no fractions in that problem yet. Okay? But there might be after we start doing stuff. Another thing that you are allowed to use is basically all the properties that you know from algebra, you can use when we're doing trig like this. Anybody have an idea of what property we're going to use in this problem first? And it's a property you use in Algebra 1 all the time.
Distributive.
Yeah, we're going to use distributive. If you were saying change to sines and cosines, you can. You're going to have to do both. So at some point, you need to change everything to sines and cosines, and at some point, you need to distribute. I like to do distributive first. So we're going to have sine times cotangent, and then sine times tangent. Now, when you look at it, you might say, well, now that looks worse. Right? Now it looks like you've got 4 trig functions. Before, you only had 3. Yeah, I would say it does look a little bit worse. But that's usually what happens before it gets better. All right, so we have sine times cotangent plus sine times tangent. Now, we could take all 4 of those and change them to what?
Fractions.
Okay, change them to fractions by converting them into... Yeah,
Sine, cosine?
sines and cosines. If you already have something that's a sine or a cosine, just put a 1 under it. That's all. You don't have to change it. Okay, so let's go with cotangent. What's our fraction we can change cotangent into?
Cosine theta over sine theta.
Cosine theta over sine theta. Okay, sine, we're not going to mess with it. It's already sine. Leave it alone. And what about tangent?
Sine theta over cosine theta.
Sine theta over cosine theta. Now, from this point, the hope is we start collapsing it. Okay, we start canceling things out. Okay, it should not get any more complicated looking than that. Okay, is there anything there that we can cancel out?
Sine theta.
Which one?
Side. Like the left top sine theta.
Right. We got to think of this as 2 isolated problems. You've got that part and you've got that part, and they are totally separate. So if you're thinking you have a cosine in the top and a cosine in the bottom, no. There's a plus sign between them. Okay, you can't cancel across a plus sign, but you can with a multiplication sign. Okay, so the first part, it got pretty nice. That's cosine theta over 1 plus, now multiply straight across. What's sine times sine?
Sine squared.
That's sine squared, just like x times x. I said x, I started to write x. Okay, so sine squared, and then the bottom, what's 1 times cosine?
Cosine.
Cosine. Okay, so we've changed everything to sines and cosines. So doing that again isn't going to help, it already is. But there's one more trick here we can use that I just told you, and we haven't done it yet in this problem. Okay?
Get the common denominator for both, and then you can cancel the cosine on top with the cosine on the bottom.
So let's find the common denominator. Okay.
Cosine theta.
The common denominator is usually the product of the 2 that you see, whether it's numbers, like I showed you on the other page, 7 and 2, or what you have there. So common denominator is cosine theta. What do we have to do to this fraction to make it have the common denominator? Nothing. So it stays the same. What do we have to do to this fraction? Multiply it by the other denominator. Right? That's how you always do common denominators. All right, so now the bottom is cosine theta. I already have that. Cosine times cosine.
Cosine squared theta.
Cosine squared theta. Okay. Now, there's something there we need to recognize.
The cosine squared is not the same as the cosine. Well, you can't, cross out the cosine at the bottom and the cosine at the top.
No, we can't do that because we got that plus sign there, so that messes everything up. If that plus sign was a times sign, then yeah, we could. But there's something else here that we need to recognize. Yep?
Cosine theta plus sine theta would equal 1.
Yeah, look at this top. Cosine squared theta plus sine squared theta. Right there. I have it as sine plus cosine. We have cosine plus sine. That's the same thing. You're just commutative property. When you take cosine squared plus sine squared and add them up, what do you get? You get 1. So that entire numerator turns into 1. So now we're left with just 1 over cosine. And looking back, 1 over cosine, that can also be written a little bit more simplified. What's 1 over cosine? Secant. And that is our final answer, secant. Okay, so that's more of a, I'd say it's more like a medium one. It had some more steps in it, not as easy as the first two. But look how much we simplified it. We started with something that had 3 different trig functions with addition and a distributive property. That's a lot going on. And we turned it into a single trig function all by itself. So secant is exactly the same as what we started with, but it's much more compact. Okay, so we had distributive property, changing to sines and cosines, common denominator, Pythagorean identity. So that had 4 steps.
On the quiz, will we have to point out which steps they are for some problems? Or like name the identity that we use?
There might be one where I say like, what would be the identity? Like if I don't have you do the whole proof out, I might say, what would be the identity to simplify the top?
Okay.
And then you just have to tell me it's the sine squared plus cosine squared equals 1.
Okay.
So in that case, you'd have to point it out. Otherwise, if it just says to prove it, you'll just have to get that answer. Yep. You'll just have to figure out that answer. And it could be like a short answer where it's just an empty box and you type in secant theta in the box. To type the Greek letter, I'll make it pop up on the screen so you can just click it. Or it could be a multiple choice question where I give you that and I give you 4 different choices, secant being one of them. And you could do it that way. All right, so any question on that one? All right, so now let's try to verify. Okay, so nice part about verify, we know the answer. The answer is the simple side. At least in this problem, I think one side is simpler than the other. What side looks like it's simpler, the left or the right? The left. So that the left side is the goal. We want to turn the complicated side into the simple side. So we're going to work with the right-hand side in this problem. You can forget about the left-hand side. That's just there to check your answer when you're done. So let's write down the right-hand side. Secant over tangent plus cotangent. So you're not going to have to do a problem that I haven't shown you a trick for previously. It's not like you're going to get one on the test and it's going to be this new trick I've never shown you. Okay, every problem is going to be one of the things. Find common denominators, change to sines and cosines. So what could we try first here?
Changing the tangent and cotangent into sine or cosine.
And I would do the top two.
And the secant.
Yeah, do them all. Change everything to sines and cosines. Okay. Let's start with secant. What is secant?
1 over cosine.
1 over cosine. And one thing that'll really mess you up is if you copied the identities wrong off the board and you accidentally do that as 1 over sine, well now it's probably going to be a mess because you're not going to get anything to cancel. Every problem is designed to have stuff cancel out unless you make a mistake. Then it probably won't. Okay, so 1 over cosine. How about tangent?
Sine theta over cosine theta.
Sine over cosine. And what about cotangent?
Cosine over sine.
Cosine over sine. Okay. So can I cancel the sines and the cosines out?
No, because they're two separate.
No, because they're addition. If this was multiplication, then yes, this whole thing would cancel out and just become a 1 in the bottom, and we'd be done. But it's not multiplication, it's addition. So we have 2 fractions in the bottom. There's not really much you can do in the top right now. The top is just a fraction all by itself. I mean, what are you going to do with it? But the bottom is 2 separate fractions. So what could we do in the bottom?
Find a common denominator.
Yeah, let's find a common denominator. So the top is just going to kind of hang out as 1 over cosine for this whole problem till we get to the end. Okay. What would be my common denominator in the bottom?
Cosine theta, sine theta.
Right, it's the product of the 2 denominators that you have, just like with numbers. You can write them in any order you want. I tend to write sine first. I don't know why, it's not even alphabetical that way, but I just write sine times cosine. And now let's start with the fraction on the left. What do we have to multiply this one by to make it have the common denominator of sine times cosine?
The opposite denominator.
The other denominator. Sine over sine. And what do we have to multiply the fraction on the right by?
Cosine theta.
Other denominator. Cosine over cosine. Okay. So sine times cosine, sine times cosine. We got the bottom. What's sine times sine?
Sine squared theta.
Sine squared. And what about cosine times cosine?
Cosine squared theta.
Cosine squared theta. Okay, so this is kind of the point where we've reached the most complex that the problem is going to get. Okay, from now it should come back down. It should start to get simpler. Still, nothing we can really do with the top at this point. But there's something we need to recognize in the bottom that simplifies a lot. If you don't see this, then you're stuck. Yeah?
The top part goes to 1.
Right. Sine squared plus cosine squared. That all turns into a 1. So that takes a big chunk of it away. So we have 1 over sine times cosine. And now we're back at a point where we've done this kind of thing before. A fraction over a fraction. How do we divide 2 fractions?
Copy off
So copy the top.
and make the reciprocal of the bottom and multiply it.
And what's the reciprocal of the bottom?
Sine theta times cosine theta over 1.
Sine theta,
So sine theta.
cosine theta over 1. And what's going to happen there?
The cosines cancel.
Right, that's multiplication. There's no problem canceling across that multiplication. So what do you end up with?
Sine of theta.
Sine of theta. And this is a problem where we can check our answer. They told us what was on the simple side. Let's go back up. That's exactly what we were supposed to get. If you got to that point and you didn't get sine theta, then that means you did something wrong. We are not going to be looking at problems that are, I guess, not true. I'm always going to give you a true statement here, and then you verify it. A step harder than this, it would be verify if possible. That means I give you something that may or may not even be true. And then you have to figure out how to verify it, or if it's not true, how to show me that it's not true. Okay. But for us, you're only going to have ones that are true. So that takes half of the thinking away, in that kind of problem. But they can get quite hard. Any question on that one? Okay. And it's a lot simpler. Right? Sine theta is much, much simpler than when we started. So far, when we've simplified identities, we got sine theta for an answer. We got a secant theta. We got, what else do we get? Another secant theta and a cosine theta. We ended up with a single trig function. That doesn't always happen. Okay? You may not always end up with just a nice single trig function by itself. And let's try that with the next one we're going to do. So we're going to do this one. Now, I've said you always should start with the side that looks more complicated. They're about the same, right? They both have a single trig function, either in the top or the bottom, and then they both have a trig function plus or minus a number, either in the top or the bottom. So it's almost like they're mirror images of each other, kind of. They're very, very similar. So is there an advantage to really changing that side into that side? In terms of simplifying it, no. There might be a reason why you want a denominator with one term instead of a denominator with two terms. I don't know. That depends on the problem. But we're not really going to see a nice simplify here. What's more important is the process of how to get from there to there, because it's going to involve this. It's going to involve conjugate. Okay, we've done conjugates before. Okay, remember, the conjugate is when you change the sign of what's in the middle. Okay? So if you had, this is where we've done conjugates. So if you had something like 4 plus 5i, we learned that the way you simplify that is to multiply top and bottom by the conjugate. What is the conjugate of 4 plus 5i? 4 minus 5i. Okay, we're not doing anything at all with complex numbers or imaginary numbers today. I'm just showing you this is where we've used the conjugate before. Now, since we're not going to have imaginary numbers, you might have something like 1 plus sign. So the conjugate would be 1 minus sign. If you had sine minus 1, the conjugate would be sine plus 1. That's what the conjugate's going to look like today. It's not going to have an I. All right, and that's the last series of tricks that I'm going to show you. So between using the conjugate, common denominator, changing to sines and cosines, and the formulas on this page, that is everything that you need to do every problem that we're doing. So now you have everything. It's just a matter of picking the right formulas to use and the right change to sines and cosines and putting it together. So let's try it on this one.
Is the numerator on the right side 1 plus?
The numerator on the right, 1 plus sine t. All right, so we can choose which side we want to work with first. I don't think it's clear that there's a simple side and a complex side. I would say they're both the same. So what side do we want to work with? The left? Okay. So then we're going to forget about the right. When we're done, we'll scroll back up. And the goal, when we're done, is 1 plus sine over cosine. Maybe that's simpler because it has addition instead of subtraction. Some people prefer that. So let's take the left-hand side. Let's go through all the different tricks. Should we try changing that to sines and cosines?
We already are.
It already is. That's not going to help. Should we try a common denominator?
There's no common denominator.
Yeah, there is no common denominator. Only applies if you have two separate fractions. This is one big fraction. Okay, so common denominator, that's not going to help. So the only thing left is to try multiplying the top and the bottom by the conjugate. The conjugate, you always look at the part that has two things in it. You're not looking at the conjugate of cosine. No. Conjugate of the bottom. Okay. What's the conjugate of 1 minus sine?
1 plus sign.
Okay, so we're going to multiply by 1 plus sign. 1 plus sign. Now, anytime you multiply by a conjugate, yes, you are supposed to distribute the cosine out, but don't do it in this step. Just leave it. Leave the top as cosine times 1 plus sine. If you distribute the cosine out, which is something you could do, you're going to be wasting time. Okay? You're going to be doing something, and then you're going to have to go back and undo it later. How do I know that? I've done a few thousand of these. That's all. So whenever you multiply by a conjugate, leave the part like that the same, but definitely multiply the conjugates out, because conjugates always cause something to cancel. All right, so now let's FOIL it up. What's 1 times 1?
1.
We get 1. And then 1 times sine?
Sign.
Sine. And 1 times negative sine?
Negative sign.
Okay, so those are gone. We had positive sign, negative sign, that's 0. Last thing is negative sign times positive sign. What's a negative times a positive?
Negative.
Negative. And what's sine times sine?
Sign squared.
Sine squared. Okay. Now, there's something there we need to recognize. Does anybody recognize something?
The 1 minus sine squared.
1 minus sine squared. We go back to what we started with. It's something that I wrote down. 1 minus sine squared is what?
The Pythagorean identity where equals 1.
Yeah, it's the Pythagorean identity. So we can turn 1 minus sine squared into
Sine squared f, or sine squared plus cosine squared equals 1. So
well, yeah, that's the original one, but how about what is 1 minus sine squared equal?
cosine squared.
Cosine squared. It's the first Pythagorean identity rearranged. So change the 1 minus sine squared to what it's equal to. Cosine squared. And watch what happens. So leave the top the same. And change the bottom to cosine squared. Now, what do the top and the bottom both have in common?
Cosine.
Right. That's on the outside, so that's multiplication, that's fine. It's not on the inside. And the bottom is just a cosine, squared. How many cosines are in the top?
1.
How many are in the bottom?
2.
2. So how many do they both have in common?
1.
They both have 1 in common. So you can cancel 1 from there and 1 from there. Now you're left with 1 plus sine in the top, and you're left with cosine in the bottom. And if you go back up, that's exactly what we were supposed to get. So again, does it simplify a lot? No. But this little trick of multiplying by the conjugate comes in handy when we have to simplify identities. Okay. Question on that one? Let's see, I don't think I had many more. Let's do, I'm just going to pick one more. Let's do, I don't know, I guess we'll finish with this one. Let's try this one. Okay, so I would say here the right side is a little more complicated because it has 2 terms in the top and 2 terms in the bottom. The left side has 2 terms in the top and only 1 term in the bottom. So I would say that this side is a little simpler. That means I'm going to work with the more complicated side, right-hand side. All Let me write that down. And sometimes what I do is I look at it and I say, well, if we change everything to sines and cosines, that would definitely work, right? So would washing your car with a toothbrush. You could. It'll eventually work. But it might not be the best way to do it. So if I start to look at a problem and I think changing to sines and cosines is just going to be too many fractions and it's going to be a mess, then I start to look at just one thing in the problem. Right? Forgot my X. What I'm looking at is just this and just that. They both already have a minus sign on the top. So that's good. That's one thing that they both have. And they both have one term here, one term there. One term here, one term there. So what I'm going to try to do is just make this one term look like that one term. And whatever I do to do that, I have to do it everywhere. Right? But all I'm going to try to do is figure out how to make that look like that. And I'm going to hope when I do that, that everything else just happens to work out nice. Okay. So what could I do to this to make it look like that? Because that's the goal. I want them the same. Yeah?
Multiplying by tangent x.
Multiply this by tangent. If you multiply that by tangent, it will become tangent squared. But you can't just do it there. You have to do it here, 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 and here. I have no idea what's going to happen with those other three. Well,
We're gonna get tangent.
what's that? Oh, tangent. Sorry, just tangent. Just multiply by tangent. Okay? I don't know what's going to happen with these other three. Well, I do. But my goal right now is I know if I multiply tangent by tangent, I'll get tangent squared. And it will at least make this one the same as that one. And I'm going to hope that all the rest just come out the same somehow. Okay? So let's do that. Okay. Actually, I'm not even using that. I did all my work up there. What's tangent times tangent?
Tangent squared.
Tangent squared. And now, what's tangent times cotangent? Okay, remember the connection between them. What are tangent and cotangent? They are reciprocals. So think in your head, what happens if you take a number and multiply it by its reciprocal?
Just one.
You just get one. Anytime you multiply reciprocals together, you automatically get a 1. Well, that's perfect. That's what we want. So we get a 1. Okay, let's look at the bottom. What's tangent times tangent?
Tangent squared.
Tangent squared. And what's cotangent times tangent? That's 1 again. So now, what looks the same on both sides? Yeah, the top. So the top looks exactly the same. So I probably don't want to do anything else with the top. But look at the bottom. Tangent squared plus 1. That's something special.
Secant squared.
Yeah. If we go back to our identities. Tangent squared plus 1. You can turn that whole thing into secant squared. So go back to our problem, and where you see 1 plus tangent squared, change it to secant squared. And that's because of the Pythagorean identity. Okay, so let's keep the top the same. And we just said that tangent squared plus 1 turns into secant squared. And that's what you have on the right. And then look what's on the left. It's exactly the same thing. So by using that trick of multiplying by tangent, you basically turn this into a 3-step problem. If you change everything to sines and cosines, I guarantee you can do it that way too. It may take 5, 6, 7, 8 steps, I don't know. But I think it would definitely be longer than that. Okay, so this is the kind of thing, it just takes practice to get used to it. Okay. So that's why there's not a ton of questions. I think there's like 10 or 11 questions, 4 through 8, 11, 12, 21, 22, and then 25 to 27. Now, they say something about graphing. You don't have to do any graphing in the homework. On 21 to 24, so yeah, 21 and 22, they say use a graphing calculator. No, just do every problem the way we did in class. So for those, don't worry about graphing. All right, and we'll take a look at those tomorrow at the beginning of class.